Alright folks, this is the first lecture on bonding, which is chapters 8 and 9 in both of our textbooks, which is amazing. And when you consider bonding, the main thing that you must consider is electrons and what they are doing. And the very first thing that you need to know about electrons and what they are doing in order to cause different bonds is the electronegativity. I'm sitting on my cord. The electronegativity is a property that different elements have, and it is that they have different values for it. They have different strengths of electronegativity, and it is how strongly it pulls the electrons to itself in the bond. They're not shared like right in the middle in between the two elements necessarily. If I'm more electronegative than you, which I think I am, I will hog all of the electrons toward myself and you won't get them very much. Yeah, I know, right? So here is a chart with really bad numbering showing the relative electronegativities. If you look carefully, folks, at the axis here versus here, it gets screwy somewhere around 3.5, but whatever. Point is, what you can see is that the most electronegative element is fluorine. And if you think about what we learned about atomic structure and things, that makes sense because fluorine is a halogen, which means it's real dang close to getting to a noble gas. So it really wants the electrons, it pulls on them hard. And it's the smallest of the halogens, and so the electrons are closest to it. So you kind of end up with this slope up to the mountain where fluorine is at the peak of electronegativity. Oxygen is next, and it's hard to tell. Yeah, nitrogen and chlorine are basically tied, and then from there it's kind of just hydrogen is sort of an exception and sort of belongs over here a little bit. He's got a value of 2.1. And it's actually interesting, there is no unit. I know I'm real anal about units, but there are no units for the Pauling electronegativity values. So you need to understand electronegativity because what we're talking about with the different kinds of bonds, when you're talking about ionic bonds or covalent bonds or polar covalent bonds, the differences between those kinds of bonds are caused by how electronegative the different atoms are. So when you're talking about an ionic bond, for example, which is the stealing kind of bond where the electron comes off of one atom and is totally transferred to the other atom and he never sees it again. This is an ionic bond, and what happens here is that you've got a very large electronegativity difference between the two elements that you're dealing with, large being greater than 2. So if you've got fluorine, which has a value of 4, and lithium, which has a value of like 0.8 or something, 4 minus 0.8, you get 3.2. That's bigger than 2, so you have an ionic bond between lithium and fluorine. So anything greater than 2 is an ionic bond, the difference between them. Now, you don't have to have the electronegativity values memorized in order to know that basically anything pathetic over here in the yellow section and anything over here in the blue section, the strong dudes, the difference between them is going to be greater than 2. You're going to have an ionic bond, and that's what we learned. You have a metal and a nonmetal, and that gives you an ionic compound. And the reasoning behind that is because the electronegativities are so different between the left side and the right side. All right, so that's ionic bonds, large electronegativity differences, and then you've got the opposite. You've got covalent bonds, which is sharing electrons. And when you have perfect sharing, which you don't get a lot, especially among children. If you had, for example, a set of identical twins, though, they would share perfectly,
Right.
let's say,
Sure they
because they would be fighting over it, but they would have exactly the same strength of fighting, and so the electrons would be shared exactly in the middle of them. And that's what you get when you have a perfectly covalent sharing bond. You have 0 electronegativity difference because it's the same atom, and the only ones that qualify for this are
salts.
no, salts are ionic bonds. Boo!
Oh, no.
Assistant loses 1 point.
No. I'm not sure.
The diatomic elements.
Oh. Sure.
So Brinkelhoff, bromine, iodine, nitrogen, chlorine, oxygen, hydrogen. Did I say that already? Oxygen again, and fluorine. Oxygen was in there twice. So if you have got a bond between elements, the two atoms that are the same element, then you have a bond which has a perfectly covalent character. There's absolutely no unevenness to the sharing of those electrons. Then you have kind of in between. You've got 0 and you've got more than 2, and then you've got in between 0 and 2, which is like 0.1 to 1.9. What about 0.11? What about 0.01? I mean, so that's a polar covalent bond, which is you're sharing, but the sharing is not fair. And you've probably experienced this at some point where I'm sharing. Yeah, you're doing a great job of sharing there, bud. I got to play with it for 1 whole minute, and you've had it for an hour.
How rude.
I know. So polar covalent bonds are between dudes that have got electronegativity differences that are between 0 and 1.9. So if you had a bond between like carbon and nitrogen, for an example, that would be a bond in which nitrogen pulls on those electrons a little bit stronger than carbon does, and so they spend more time near nitrogen than they do near carbon. And so you have a slightly negative E charge on nitrogen and a slightly positive E charge on carbon. And so that bond is polar. Finding out if the molecule that it's a member of is polar is a much different business, and we won't get to that for a little while. But that's the idea. That's why you've got to understand electronegativity, the ability of those elements to pull the electrons toward themselves. Different strengths result in different types of bonds. Woo. All right. We're going to spend a little time on ionic compounds and bonding, and then we're going to spend the rest of the whole unit mostly on covalent stuff. So here's the ionic bit. When you have ionic compounds, you have got a cation and an anion. The cation is positive, and the way that you remember that is that cats have paws.
I remember it because there's a T in it. Cat. T looks like a plus.
There's a T in anion.
Electric graduate college?
So a cation, a positive ion, and an anion, a negative ion. The cation is formed generally by the metals because the metals don't love their electrons, so they give them away happily. The anions are formed by the nonmetals, and they suck up electrons like nobody's business. And that's generally a metal and a nonmetal. However, you can get the polyatomic ions, and then you can say, well, ammonium is not technically a metal. Okay, fine, it's still a cation. And the ionic compounds are known for forming crystals, beautiful little pretty crystals, with a lattice structure. And now I have gotten a picture of a crystal lattice using a Google search, which is right here. And the crystal lattice structure, this is the simplest version that you can have. You've got your, let's see, which one of these is bigger, sodium or chlorine? Sodium is bigger, so the green dudes are sodium and the purple dudes are chlorine. And what you end up with is a cube that goes sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine. And then in the next dimension, sodium, chlorine, sodium chloride, sodium chloride, sodium chloride, because they're ions, right? The sodium cation, the chloride anion, the sodium cation, and it goes all the way, and it makes cubes. And that's just because of the way that these size spheres pack well. If you have different size spheres, you end up with different packing, and you can get different shapes of crystals, like pointy hexagon things. And anyway, that's why salt is cubes. So if you ever pour out salt and look at it very carefully, it is actually like really nice, pretty cubes, because it's giant, these guys. Which is why you don't really say that salt is a molecule, because, like, is that whole cube a molecule? Not really. No. So there you are. And yeah, hey, I got it right. Look, the chloride is bigger. Why is the chloride bigger? Because it has fewer protons. Because it has fewer protons. It's in the same period, but it has fewer protons, so it's not pulling them in as hard. All right, boom. So the crystal lattice structure, that's what that looks like. You're familiar with forming the formulas. That's found by crossing the charges, and that's something you should be familiar with. For example, you do you know, magnesium and fluorine. Magnesium, the ion is 2 plus, fluorine is, don't you do that to me, I'll kill you, minus, and you cross the charges in order to figure out that the formula is MgF2. All right, ion size. Like I was saying, the crystal lattice, the size of the ions matters as to how they pack into the crystals, because if you have dudes that are generally the same size, you get kind of a nice cubic shape, but if you have giant, tiny, giant, tiny, giant, tiny, then the tiny dudes can kind of fit in between the little bumps in the giant guys, and so it makes for different stuff, and there's a whole lot of stuff that we could go into. But it's important, the size of the ions, because the closer they can get, the more energy you can get out of the lattice forming, and so we need to understand a thing which is isoelectronic ions. Iso means same, so isoelectronic is the same electrons, ions, and what you end up with is little runs of ions that have got the same electron configuration because they're all trying to be like the noble gas that's nearby. Oh, it's late. So oxygen is 2 minus and fluorine is 1 minus, and they have got the same electron configuration as neon. Well, but so does sodium and magnesium and aluminum, 1 plus, 2 plus, and 3 plus. So this little series, boom, 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 is an isoelectronic series. Those 5 have all got the same electrons. And what you see is that it's big, small, 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 small. The biggest one is the one with the fewest protons for that same number of electrons because it doesn't suck in as hard, the attraction between the positives and the negatives. Then you go down a row and you've got another isoelectronic series, sulfide, chloride, potassium, calcium, and gallium ions have all got the same electrons. They're all slightly larger than the dudes above because they've increased in the number of shells that they're, so they're on 3, are they on 3 or 4? 3, they're on 3. But again, you see that pattern where the biggest one is the first one because it's got the fewest protons for the same number of electrons. All right, so that's isoelectronic series, boom, 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 and then the dudes that they didn't make it on the chart. This is important also for a thing called lattice energy. The reason that you make these nice crystal lattices is because they're charged. And you know, if you've ever played with a bunch of magnets, they attract each other. These are basically little magnets, so you have a little positive magnet and a negative magnet. And so the positive magnet surrounds itself with negative magnets, and the negative magnets surround themselves with positive magnets, and so you end up with this crystal structure because they're kind of arranging in the best possible way for you know, energetically being close to the dudes they want to be close to, and that's how you end up with this thing called lattice energy. After the first couple of steps of forming an ionic compound, which is getting the electrons to the element they're supposed to be on, then those charged ions are like, hey, I'm positive, hey, I'm negative. Okay? So they attract each other, and that releases energy because it's much more stable to be close to each other when you're a positive and negative than to be far apart. So this lattice energy, which is exothermic when you're forming a crystal, this formula, you don't have to use it, but you have to understand what would make it bigger or smaller. K is the constant. You can ignore the constant. Goodbye, constant. That would just make the numbers and units work out, so neener. But the 2 variables that are important for determining how big your lattice energy is Q and R. R is the radius, so that's one that actually makes sense. Stop erasing my writing. That's one that actually makes sense because if you have got a giant ion and a tiny ion, they can't actually get their centers super close together. They go bonk, 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 bonk. So the bigger they are, the larger the radius, and then you're dividing by a large R. And when you divide by a large number, you end up with a small number. So if you've got teeny little ions, then you have a much larger lattice energy. So if you, for example, formed something with oxygen and sodium, so sodium oxide, versus sulfur and potassium, potassium sulfide. The one that would have the larger lattice energy would be the one that's smaller. So that's going to be sodium oxide. So you're going to get more energy out of making sodium oxide than you are from potassium sulfide, because you end up with a smaller R, and so a bigger lattice energy. The other thing are these Qs, and this Q is for the charge. So for oxygen, the Q is 2, and for sodium, the Q is 1. And what it's saying is, bringing charges of 2 close to each other gives you more energy than bringing charges of 1 together, because there's more of an attraction. So if you've got 2 times 2, that's way bigger than 1 times 1, and since it's on top, you end up with a larger lattice energy when you have stronger charges. So magnesium oxide versus sodium fluoride. Magnesium and sodium, magnesium is smaller, sodium is larger, but oxygen is larger and fluorine is smaller. So magnesium fluoride versus sodium oxide, wait, no, what did I say?
Magnesium oxide.
Magnesium oxide and sodium fluoride. This 2 charges of 2 versus charges of 1, the magnesium oxide is totally going to win, and you get more lattice energy out of that one. So those are your 2 factors for how much lattice energy you can get out. Ding. All right, so here's an example of all of the steps and the energies of forming ionic compounds. And the one that we're going to do is magnesium fluoride. How about that? So here is, you should recognize this. Did you watch all my thermodynamics videos?
Yes.
So the enthalpy of formation, you know about that one?
Yes.
This is your standard enthalpy of formation formula for magnesium fluoride, because it is made out of its constituent elements, magnesium and fluorine. So when we get this answer, it should match what's in the back of the book, so I'm going to go check that, I guess, when we're done. That would be cool. All right, so first you've got to make the electrons right, and then you let them attract. So the first thing is to make this guy hot, because when you're pulling electrons off of magnesium, you can't really do it until you get it into the gas phase. So first, you've got to heat magnesium from solid to a gas, and that's the enthalpy of sublimation of magnesium, which is written down in a chart somewhere, and that's 150 kilojoules per mole. So we're doing that. First, make that really hot. Next, pull his electrons off. No! We're doing it. Pull 1 electron off of magnesium. Now, there's something that we've actually studied, which is the energy required to pull an electron off of something, which is the ionization energy. And that's written down in a chart. So you go look that up, you pull off the first electron, that's the first ionization energy of magnesium, and that is 735 kilojoules. It takes that much energy, it's endothermic, to pull that electron off. Now the second one is harder. You have to pull an electron off of the magnesium plus ion. That's the second ionization energy for magnesium, which is 1445. All right, so now you have this poor electronless magnesium in the gas phase and a couple electrons floating around. So the next thing we got to do is with fluorine. Now fluorine is thoughtfully already a gas. Thank you, fluorine. So we don't have to sublimate it. You've got to break it. So you've got to break the bond in fluorine. This is endothermic. It takes energy to break a bond. Chop. So that's the bond energy between a fluorine and a fluorine, and that's in a chart. It's a different chart, but it's still a chart. And that's 154 kilojoules. The next one that you've got to do is you take one of those floaty around electrons and you jam it onto the fluorine. Now this is actually exothermic. Yay, because fluorine loves this. It makes him happy. So you take that electron, you put that on. We learned about something, which is, how much energy do you get out when you jam an electron on? That's the electron affinity. This is why we learned this. The electron affinity of fluorine is negative 328. So when you jam an electron onto a fluorine atom, you get 328 kilojoules out. You're doing it twice because you got 2 fluorines, that time and that time. And then here's the big one. Are you ready for the big one?
Maybe.
The big one is Now you have created magnesium 2 plus ions and fluorine 1 minus fluoride ions in close proximity to one another. And when they are in close proximity to one another, they attract each other. And Gertrude. So they don't know what that is.
No,
So that's the lattice energy of magnesium fluoride. Why isn't there a 2 there? 2, because it eats my 2. MGF2. So the lattice energy of this is negative 3916. But that's the big one. It comes out really big. You get a lot of energy out when you let those charged ions attract each other and form a stable thingy.
Bond.
Sure, bond. An ionic bond. Let's call it an ionic bond. That's what it is. And so our total HF is, oh, I don't know. I'm going to have to pause it and add. And the answer is, drum roll. It's a terrible drum roll. Negative 2,088 kilojoules per mole. So what that means is when you make magnesium fluoride, you get a whole buttload of energy out. And that is all we were doing with ionic things.
Okay.
All right, covalent bonds, which, if you remember, are made when you have got small or zero differences in electronegativity, result in the sharing of the electrons between the two atoms. And this is when you share the electrons, it's a stabler state, it's a lower energy state. So forming that bond is exothermic. Because they were in kind of and so that energy goes out. If you're going to break that bond, you have to pull them apart and make them neurotic again. So you have to give them energy to break a bond. So that's an endothermic thing. Let's see, it requires energy to break, relate. One thing that's cool that's actually related back to the previous unit in thermodynamics is that there is a table of average bond energies right here, which basically tells you how much energy is required to break all these types of bonds. So let's say you want to break a bond between hydrogen and hydrogen. That takes 432 kilojoules per mole. Let's say you want to do that between hydrogen and fluorine. It takes 565. Something to notice is the differences between single bonds and double and triple bonds. So if you've got a carbon-carbon single bond, that takes 347 kilojoules to break that bond. A carbon-carbon double bond requires 614. It's a stronger bond. It released more energy when it formed, and so it takes more energy to break it. Is there a carbon-carbon triple? There is. There's a carbon-carbon triple bond over here, which is hard to see. And that requires 839 to break it. And then the killer one here is nitrogen, which requires 945. Which is why it's really hard for plants to get nitrogen. Like, most of the air is made out of diatomic nitrogen molecules, but it takes 945 kilojoules to break those apart and grab the nitrogen in order to use it in the proteins that you want to make when you're a plant. And you are. So we tend to spray the ground with ammonia fertilizer, where we have already gone in and broken the bonds for the little plants, and they're like, yay, nitrogen in a form I can use. But if you are a legume, and you are, a legume. If you are a legume, you have bacteria that live in your roots, and they have got an enzyme that makes it really easy to break this bond. And so they'll just sit down there chilling out, breaking that bond all day long and providing nitrogen to the plant. And that is why beans and peas, which are legumes, are high in protein, because they can make protein like crazy, because they can get hold of nitrogen because they're growing bacteria in their roots. Ding! Biology. Based on chemistry. So, point is, oh, and the other point is, these are average. They tend to be a few points off for specific ones that because of the interaction of other atoms in there pulling on things. Don't be surprised if something is slightly off compared to your delta HF formation that you have in the back of the book. So, yes, here, the energy. Sorry, it's late. A triple bond has got more energy to it than a double than to a single. And then the other thing about it is the length, is that a triple bond is a really short, like physically short bond. It pulls those atoms closer together compared to a double bond, which is close, compared to a single bond, which is long. So very short, short, and long. Ding. Very strong, strong, and weak. And using that table of bond energies, you can actually estimate your exothermic versus endothermicness based on, okay, well, it takes this much energy to break all these bonds, and then I get this much energy when I form all these bonds, and I'll subtract them, and neener, I end up with this much energy. And this is a pretty good estimation of your delta H of reaction. It's only pretty good because, again, the table can be a few points off depending on which chemicals you're using because they're average values, but you'll get a pretty good idea. So here we go. The delta H is the sum of all the broken bonds minus the sum of all the bonds that you've formed. So here we go. The bonds that we broke. Well, N2H4 looks like this. N, don't steal my drawing. And we are going to break 1, 2, 3, 4 bonds that are NH bonds, which are worth 391. So that's going to be 4 times 391. And we're also going to break this bond here, which is the single bond between nitrogen and nitrogen, which is worth 160. Here, be my calculator slave. Put that in there.
Do a single bond or a double bond?
It's single.
Okay.
Because, is it supposed to be single? It's not supposed to be single.
It's a double bond.
It's a double bond? 2, 4, 6, 8. Yeah, we gotta have the octet rule. Fine. Give me that. Give me that. It's not 160. Don't be silly. Where is it? Nitrogen, nitrogen, double bond. Here we go. 418. Don't be silly. It's not 160. Yes, it is. It's 418. So 4 times 391, and then plus 418. That's the bonds that are broken. Oh, but we have to do the fluorine ones too. We also have fluorine. And oh, don't forget your dots. That's this bond here. That's a fluorine bond. Where are you, fluorine? Fluorine. There you are, fluorine. 159, but there's 2 of them because we got 2 moles, so 159 times 2. Add all those suckers together, what do you get?
2300.
2300, that's really round. And then the bonds formed, we're going to have nitrogen with a triple bond, which is the big sucker, which is 945, and 4 times the hydrogen fluorine bond, which is 565. All those together, what do we got?
3205.
3205. All right, so this is broken minus formed, so that's 2300 minus 3205. And what does that give us?
905. Negative 905.
Negative 905 kilojoules per mole. So that's how you use that formula. Ta-da!
Woo.
Yay! All right, and that's that for this page. And here are the questions. And go ahead and do them, and then come back and check your answers against mine. All right, folks, these are easy. The lowest to highest electronegativity, you should know that fluorine is the highest. Oh, I do want my black screen because this screen keeps taking away my pen. Nearm, nearm, nearm. Bing, black screen. This screen does not eat my pen. And this thing here, pen. Yes, all right. So the highest electronegativity is fluorine, and if you go and look at your chart, you can see that sulfur is behind it, and then arsenic. Then this one, oxygen, lithium, and boron, you know that oxygen being the nonmetal, and then boron, and then lithium. Woo. That's not hard, honestly. The least to most polar bonds, this is going to be all these guys with fluorine. So the guy that's closest to fluorine and then the guy that's farthest from fluorine. So the guy that's closest to fluorine is carbon, so this is the least polar. That's number 1. And then the one that's farthest from fluorine is germanium, so that's the most polar, and you're in the middle, Mr. Silicon. And then all these dudes with sulfur, the fluorine, the chlorine, and the bromine, you go and look, and you see that bromine is the farthest, so it is the most polar, and then this one is the least polar. Yeah. Pew, pew. 1, 2, 3. Bam. 3 ions that are isoelectronic with krypton and arrange them in order of increasing size. Krypton is... Did I do that one wrong?
You said number them from least to most polar.
So least polar... Where's my periodic table with the little picture? Come here, picture. Sulfur and fluorine. So that's sulfur and fluorine, sulfur and chlorine, sulfur and bromine. Okay, so sulfur and bromine is the least polar.
There we go.
Yeah.
Yeah.
So that should be 1.
We said it wrong.
Okay.
We called it the most polar.
So that's the least polar, the second polar, and the most polar.
There we go.
Okay. Thank you, assistant.
I get
All right.
my point back.
You get your point back. 3 ions that are isoelectronic with krypton. Krypton lives, so we've got neon and argon and krypton. So krypton lives here right next to bromine, and so ions that are isoelectronic with krypton would be, say, selenium, bromine, and then rubidium and strontium. That is not what I put.
Remember, this chart is off.
Yeah, it is off. Let me go look at my real periodic table. With krypton. Yeah, selenium, bromine, rubidium, and strontium. No, I just answered it wrong there. So, what did I say? Selenium 2 minus bromine minus and rubidium, let's say, plus. Increasing size, so the big one is going to be selenium because he's got the small, so this is, I did it backwards. Increasing size. Alright, which compound, sodium chloride, I said these were easy, so I keep getting them all wrong. Sodium chloride or potassium chloride would have the more exothermic lattice energy, and why? And you've got to remember that formula Q1, Q2 over R. So what's important is the radius or the charges. And if you look here, this is +1, -1, +1, -1. So your Q's are the same. The difference would be in the radius, and so then the question becomes between sodium and potassium, which one is bigger? Because if it's bigger, then it can't get as close, and so your radius is bigger, and so then you have a smaller lattice energy. So the bigger lattice energy is going to be the small dude. The small dude is sodium. Bam. All right, which compound, barium chloride or barium oxide, would have the more exothermic lattice energy? Again, same formula. You've got barium, which is +2 charge and -1, and then +2 and -2. And so you end up with 2 versus 4. And so because oxygen has got a stronger charge than chlorine, you end up with a more exothermic lattice energy. Woo. All right, use the following to estimate delta H of formation for sodium chloride. All right, so first you have got to heat up sodium. That is this guy, so that's 109. Second, you have got to pull electron off of sodium. That's 495. Third, you have got to bust up chlorine. That's your bond energy. So that's the 239. Then you've got to... Did I already rip the electron off? I did. And now I need to jam it on. I need to jam my electron. That's the electron affinity of chlorine on. 349. And then my lattice energy, I've got to add that on there, -786. What? You just have to add them all together? This is too easy for you. Well, anyway, add them all together and you get negative 292 kilojoules per mole. Woo!
Do you have to do anything with the 1/2?
No, the 1/2 is just so that you end up with 1 sodium and 1 chlorine. Oh wait, yeah, hey, what? Yeah, you do have to do something with the 1/2. I'm so wrong. This is wrong. Thank you, assistant. That's what I get for saying these are easy. Yeah, you do get a point. This, the 239, is for a mole of chlorine. So you've got to divide that by 2. So, now I don't have the answer written down. 109 plus 495 plus 239 over 2 plus negative 349 plus negative 786 is negative 411.5. Thank you.
Welcome.
You're very good. Negative 411.5 kilojoules per mole. It's not a great box. All right, use bond energy values from the table above to estimate delta H for this thing. All right, so we've got N2. It's helpful to draw them. There's your N2, so we've got to break a triple. That's that 945. And hydrogens. That's 3 of those, and you end up with a couple of NH3s. So that's 6 times, what's the number for NH? Here it is, 391, 6 times 391, and then what's the HH's is 432, 3 times 432. Is that what I did? Yes. So I'm not crazy. Maybe on this one. And that gives you, I think, negative 1068, because that's bonds broken minus bonds formed. Broken minus formed, broken minus formed. So here's the broken. So 945 plus 3 times 432 minus 6 times 391. And sorry, I shouldn't have had that answer already. 1068 kilojoules per mole. And this has been my haphazard answers for these questions. Thanks, folks.